Yeah, let's get started. Someone asked in the or some reflections that there were some problem, or at least one problem in the homework, where you had a different, it was a tank problem. We have a different rate in and a different rate out. I'm looking at the homework and I see one like that, but I will point out you're not being actually asked to solve it. So we can certainly talk about how you would set that one up, but I don't think you're going to be asked to solve a problem like that. So I don't think it's worth our time to do that. I'd be happy to do it some other time if someone really, really wants me to. Although again, I don't imagine you're going to be asked to do that. But let's talk about it. So I'm looking at problem number 12 from the homework. Here's my specific setup. A large tank contains 300 liters of a salt solution, which has a concentration, interesting, of 0.3 kilograms per liter. A salt solution is, a salt solution which has, so many words, a concentration of 0.45 kilograms per liter is added to the solution at a rate of 60 liters per minute. At the same time, we just got darkened. It's like the sun really wanted to say. At the same time, the solution drains at 65 liters per minute. So what we're being asked to do, two things. We'll do a few more than that. But the first part of this is to set up the differential equation. A couple of things here. So we should note that we're going to say that S of T equals, and this is where it's really important to be aware of what we're talking about, not the concentration, but the amount of salt in the tank at time T. Yeah, I think I'm sorry. Just the backwards. Well, the fun is not too terrible. It's kind of terrible.
Can you do it like halfway? Or?
That is halfway. Here's the front half, which is even worse. Yeah, halfway is the back. It's the front. It's like 2/3 in the back or 1/3 in the front. Yeah, I guess we'll just live with sitting in the dark. So to set this differential equation, we're going to say that ds dt, that's the rate of change of the amount of S, is equal to, I usually like to write, it's the rate in minus the rate out. I think my teacher's been writing the amount in minus the amount out. Same idea. It's how much we're putting in minus how much we're taking out. The in part is usually the easier part to deal with. So when I'm thinking about this rate in minus rate out, I'm really thinking of it's the concentration of the solution going in times how fast we're putting that in. So let's see, the concentration that's going in is 0.45 kilograms per liter. And then we're putting in at a rate of 60 liters per minute. My calculator. Let's see. There. So now I got it. So and really it doesn't actually. The rate out part here is always the more challenging part. So we know that we're draining this. Well, actually, we should talk about the concentration first. So the concentration of the tank is how much salt there is, which is S or S of T if you prefer, but I'm right S. So S kilograms divided by the volume of the tank. And here, what makes this different than our previous setups is that the volume of the tank is changing. We're putting solution in at a rate of 60 liters per minute and taking out at 65 liters per minute. So every minute we're losing 5 liters. So we're starting off with an initial volume of 300 liters. And then every minute we're going to subtract off 5 liters. So we're going to subtract off 5 times T, where T is measured in minutes.
300.
Correct, it's 300 minus 5T. And then multiply by how fast we're taking that solution out, which is 65 liters per minute. Let's go do this here. So that's going to end up being that ds dt is equal to 0.45 times 60 is 27 minus, I would write this as 65 times S over 300 minus 5T. Yeah. So the 5 is coming from the difference between the 65 liters per minute that's going out and the 60 liters per minute that's going in. So every minute we're going to lose 5 liters. So when T equals 1, we've lost 5 liters, and so the volume is now 295. When T equals 10, we've lost 50 liters, so the volume is 250. This one definitely, yeah, definitely. I was about to say definitely, maybe. This one probably has to be done with the first order linear. So if you were going to, we're not going to solve this because it's a little more complicated. But if you were to solve this, in fact, let's talk about how you would set up the solving. Although we're not going to finish it probably. So to solve, we would rewrite this as ds dt plus this part here, the 65 over, I'm going to write it as 65 over 300 minus 5t, 5t times s equal to 27. And so this is the usual kind of setup. Here's my, essentially my y prime. Here's my p of t times y. Here's my q of t. So then we would find the integrating factor. Our integrating factor would be e to the integral of that mess there, 65 over 300 minus 5t. Which actually probably isn't too terrible to solve. Because it ends up being somewhat not too often. But that's not really the point of this question. So I don't think we don't need to continue with that right now. I will point out 2 other things that are asked here. So the first question, I actually lost the place for 1 second. So they do ask us at t equals 0, what is s of 0? And this question is really just getting at making sure that you understand the difference between what s represents and what we're being told. We're being told that the initial concentration of the tank is 0.3 kilograms per liter. And we're told that the tank initially holds 300 liters of solution. So our S of 0 is just going to be the amount of salt at the beginning, which is going to be, well, the concentration of 0.3 kilograms per liter times the total volume, which is 300 liters, which ends up being, what, 90 kilograms of salt? That's what might make that question a little trickier than you might normally think it would be. So again, I'll say, this is pretty generally true, that when you're talking about these problems, you're always talking about the amount of stuff that you have in the tank or in wherever, not the concentration of that stuff. The only other question I could see asking here, without actually solving it, would be, how long does this process continue? Or in other words, how long until the tank is empty? Well, we're losing 5 liters every minute, and the tank started off with 300 liters. So I think we just have to do 300 divided by 5, which is going to be 60 minutes. So exactly 1 hour. Cool. Right, because every minute we're losing 5 liters. So, yeah. All right, Let's look at a couple more word problems just because people had asked for some more examples of word problems. I really think the hard part about the word problems is the setup. So that's what we're going to focus on right now. So let's look at something like this. So yeah, and I am taking problems from the homework just to kind of talk about the setup, not so much the solving. Let's look at, yeah, sure. This is number 13. A wet towel hung from a clothesline loses moisture. Well, through a big space there, James. Loses moisture at a rate proportional to its moisture content. Or in other words, the more moist it is, the faster it will lose moisture. The less moist it is, the slower it will lose moisture because of proportionality. If after 4 hours, the towel has lost 30% of its moisture, how long until it will have lost 50%? I'm going to change that last part. How long until it will have lost 65%? We're probably not actually going to finish this problem, but we are going to definitely do the setup and talk about what we're doing. So before we get into this question, we have to actually find, let's call it M of T for the moisture at time T. Unless they have not given it. Moisture as a percentage at time T. We have a couple additional, we'll talk about them in a minute. So here's what we're given. We are given that the rate of change of moisture, dm dt, or d whatever dt, right? The rate of change of everything is always d that thing over dt. We're told that it's proportional to the moisture content. So that's just going to be some constant times the amount of moisture. This is a pretty standard differential equation. You might have seen this enough that you just what the solution looks like. I will, in fact, yeah, I think it's worth. So this one's, we're probably going to solve it because it's not too terrible. I'll point out that when you have this specific situation, you're automatically going to end up with M of T equal to C e to the KT. That is the standard typical solution for when the rate of change of something is a multiple of that same something. You could also solve it though, right? We could definitely solve this by saying 1 over m dm is equal to k dt, and then integrating both sides and getting the natural log of m equal to kt plus c, and then exponentiating both sides and getting m equal to e to the kt plus c, which then becomes e to the c times e to the kt, which is just a new constant times e to the kt. So it really is the same answer. Yeah, I said we weren't going to solve it. I'm totally going to solve it, right? Because there is something I think that's worth mentioning here. So we're given a couple initial conditions. We're given one of them explicitly, and the other one is kind of implied. So we know, so we've got the following. We know that M of T equals C e to the KT. And here are some initial conditions. We know that at time equal to 4 hours after we observed it, the amount of moisture that's been lost is 30%. Okay, but that's not what this says. This isn't telling us how much moisture we've lost. It's telling us how much moisture we have. So after 4 hours, the amount of moisture remaining should be 70% of the initial. So that's where things get kind of weird. Yeah, how am I going to write this? There's a couple ways you could go here. My preference is typically to say in the beginning, I like to pick an amount I'm starting with. I would personally choose to say that time equals 0. M of 0 is 100. Or if you like 100%. I guess percent might make more sense here because we were talking about, right? It's 100% moist. You wouldn't really say it's got 100 moisture units, but whatever. So then 4 hours later, if it's lost 30% of its original moisture, it still retains 70% of its original moisture. Just make sure that when you're writing things down here, you're always writing things down in the terms of how much stuff we have, not how much stuff we've lost. So these are our two initial conditions. This is the one that I was kind of trying to say is implied, that we don't explicitly say that we start off with 100%. We just kind of know that, oh yeah, we're starting off at the beginning observation with 100% of the moisture that's observed. And then the rest of this is not too terrible. I would start here and say that M of 0 is C e to the k times 0, which is equal to 100. You're going to end up getting C equal to 100. And you could write percent if you wanted to. I think we don't need it. We can just know it means percent. And then M of 4 is equal to C, but C is 100, e to the k times 4. And that's equal to the percentage of moisture remaining. And then we can find K. You get e to the 4k equal to 70 over 100, which is 0.7. So then 4k is equal to the natural log of 0.7. So then k is equal to 1/4 the natural log of 0.7. So then you've got the model, and I'll say usually, so the model, aka the solution, that's often what we're looking for. So the solution / model is that M of t is equal to 100 e to the 1/4 natural log of 0.7 times t. I guess I could say percent. So if t is 0, we've got 100% of the moisture, and as time goes on, we have less and less percentage of the original moisture. And then lastly, if we wanted to solve the question that was asked, which is how long until we have lost 65%, be careful here. We don't want to do this. We don't want to set M of t, which is 100 e to the 1/4 natural log of 0.7 t equal to 65. Because we're asking how long it takes until you've lost 65%, which means what? How long until we have remaining 35%. So sometimes problems like this try to be, I would say, kind of tricky with the language that they're using. Make sure you're always thinking about how we want to be talking about how much stuff we have, not how much stuff we have lost. Questions on either of these? Let's try and do one more word problem, but we'll really actually just do the setup. Maybe. And then we'll talk more about some 3D graphing stuff, because that's definitely where we're moving. We have moved towards, but people were asking about, see those, make sure. Yeah. People were like, let's see some more problems. Okay, let's see some more problems. So let's see here. Yeah, I like this one as well. This is similar to number 8. So during a chemical, and I'm just gonna, so here's what I'm gonna say. I'm gonna read the words of this problem and I'm gonna write down what I think is important. So during a chemical reaction, substance A is converted into substance B at a rate that is proportional to the square of the amount of A. So I'm gonna write down A turns into B at a rate proportional to the square of the amount of A. So to me, it looks like, I feel like this B part really isn't super important. Like they're saying A turns into B, but really we're just caring about the rate of change of A. Let's read the more of the question before we fully decide on that. Let Y be the unconverted amount of substance A at any time t. Okay. y is the unconverted amount of A. Annoying. When time equals 0, and then they're just giving us some initial conditions. Time equals 0, y equals 50, time equals 1, y equals 20. Find y as a function of t. So to find y as a function of t, we need a differential equation. All right, so yeah, what's y? Well, it's the amount of A that isn't converted, right? So how are we gonna write that down? Good question. Like, and I'm really asking because, like, I'm just thinking about, like, well, what are we really doing here? We know here's what I'm thinking about. I know that the rate of change of A, I know that dA dt is equal to some constant times the square of the amount of A. That might be helpful, might not. Y is the unconverted amount of A. So I guess Y is equal to, I don't love the way they phrase this. Yeah. Good question. Yeah, maybe. I honestly don't really know, right? It's kind of funky. So what I'm thinking is that I know that at time equals 0, y equals 50. And the amount of A that has been converted into B is 0. So to me, it feels like A and B have to add to 50. Right? Does that seem plausible? I think so. Because we're starting off with 50, and they don't say that we're like losing stuff. We're just saying one of them turns into the other. I feel like in these problems, sometimes there's a lot of like chemistry kind of assumptions in the background that aren't really getting fully explained or thought about. We're just saying, yeah, this thing turns into that. We're not losing anything. We're not gaining anything. So I think we should be saying something like, well, we know that A plus B equals 50. But yeah, why? I mean, so I feel like, what do I feel like? I feel like it's kind of funky.
Would it still be dA over dt because, like, as time increases,
Mhm.
y increases?
Right, as time increases, y is going to decrease, right? So I think what we want to do, and I'm not 100% sure, but the way I am imagining this, I think we want to think of y as being 50 minus A. Here's why. At time equals 0, so when time equals 0, A equals 0, y equals 50. That seems reasonable, right? And then the equation that we're going to write down is that, well, I think I can say A equals 50 minus y. So really I want the rate of change of 50 minus y to equal the rate of change, to equal k times 50 minus y squared. It feels funky. I feel like I'm leading you astray, to be perfectly honest. So good question. Setting these up is hard, right? Like, it's not always super easy to identify what's happening. I feel like this, I feel dicey about this, to be very honest. Yeah, I don't like this question. I looked at this one and I was like, oh, maybe. And I was like, I should have just avoided it, but I didn't. So, right. Y is the unconverted amount. So we know that the rate of change of A is proportional to how A squared. So it should be that, I feel like this is fine. Yeah, I don't feel like this is wrong. I feel like the rate of change of 50 minus y, which is just what A is, the amount that hasn't been, the amount that.
Would you just solve it for dA dt and then
Maybe. Yeah, that's probably, yeah, I like that idea better. That's a good idea. So let's scratch this. Yeah, I think you got the right idea. So we can definitely solve this, which is not too bad. We can say that, I know, all right, so we're just gonna set it up once again, not just setting it up. We have that 1 over a squared times dA is equal to k times dt. I feel like we see 1 over a squared enough that you should get used to seeing that, oh, we know that the antiderivative of 1 over a squared is negative 1 over a. And on the right-hand side, again, we have a kt plus c. So then we can solve for a. So watch this real quick. I'm going to multiply both sides by -1. I think in class she actually does multiply by -1. You can get away with not doing that, but let's go ahead and do it that way. So 1 over a is equal to negative kt minus c. And then we take the reciprocal of both sides. So that the a as a function of t is equal to 1 over negative kt minus c. And I think what we say is a is 50 minus y. So we could just replace this with 50 minus y equals 1 over negative kt minus c. Yeah, that seems a little strange though. I mean, strange, not wrong, just strange. And if you want to solve for y here, we can say that y is equal to, I'm going to just think about adding y to the right side and subtracting this over here. So y is equal to 1 over positive kt plus c is 50. Seems interesting. Let's see what we might as well, we've gone this far, we might as well finish it. So here's what we know. We know that at time equals 0, y equals 50. Well, that already seems problematic. Here's why. This fraction here is never 0, which means clearly I've done something incorrectly, right? Because this can't, with the way we're writing here, this can't be the solution. That's a bummer. Now I'm not sure. Yeah, I think I should think about this one and come back at you with it, because I can stand up here and be like, well, let me think about it some more, but really, like, I'm actually not sure. I know I've done this problem before, but I forgot to do it. So I'll think about that. Maybe I'll write something and post it on Canvas a little bit later today, because yeah, I don't remember how this one goes. I'll try not to think about it. Okay, let's give ourselves the last 20 minutes of class here to talk about traces specifically, because I think those are important. Yeah, grab that. Sorry about that. So, sketching things, finding traces. Let's talk about some equations of quadric surfaces, which sometimes people mistakenly say is quadratic, but not, it's actually quadric. So there's like 6 of these, and you might have already seen some of them, but let me give you an example of one of them. So let's say we have the following surface. We have, sure, let's say we have, sorry, I'm trying to pick which one. Yeah, let's do that one. Okay. So z equal to y squared minus x squared. So this is an example of one of the quadric surfaces, and the way we would usually graph something like this is by drawing the traces in each of the planes. So let's draw some traces. So we'll start, and one of the, so sometimes one or more of the traces is kind of funky. That's going to be the case here. Let's actually not start with the trace in the XY plane. That one's a little bit weird. So we start with the trace in the YZ plane. If I'm in the YZ plane, which I know, what's your name by the way? Emery. I knew you weren't here last Friday, but I talked about how in the classroom I'm going to think of that corner as the origin, and that wall is the XZ plane, the floor is the XY plane, and the wall behind me is the YZ plane. Which I like because the YZ plane I'm always thinking of as the easiest one to graph in, because the YZ plane is the one that's kind of like just flat on the paper. So the YZ plane, we're setting the missing variable equal to 0. And we're going to get z equal to y squared minus 0, which is just a parabola. It's in the yz plane. We've got this upward opening parabola whose vertex is at the origin. Let's look at the xz plane. Well, there we're going to set y equal to 0. And we're going to get something very, sorry. No, y equals 0. We're going to get something very similar. We're going to get z equal to negative x squared, which is not quite the same. It's just a downward opening parabola. So far, here's what I've kind of got. In that corner over there, I've got an upward parabola going this way and downward parabola going that way. And then we should talk about, even though it's kind of annoying, in the xy plane, when we set z equal to 0, we're going to get 0 equal to y squared minus x squared. We have to be extra careful here because we get a little bit more than you might think we do. If we bring the x squared over to the other side, we get x squared equal to y squared. And if we take the square root of both sides, we don't just get x equal to y. When we take the square root of both sides, well, you might notice that x or y could be positive or negative. Y could be 3 and x could be 3, or y could be 3 and x could be negative 3, or x could be 3 and y could be negative 3, or both of them could be negative 3. Right? They can kind of both be any sort of positive or negative of each other. So this equation actually boils down to being the absolute value of x equals the absolute value of y. Or in other words, y equals x or y equals negative x. So when we graph this, it's kind of weird. You get these two lines. And if we want to try and put it all together, yeah, let's make it big. We're going to put it all together on one big graph. Yeah, and we'll talk about some level curves as well. Okay. So here's our x, y, z coordinate system. And I'm going to draw my traces in each of the appropriate places. So in the YZ plane, so I'm always going to try and draw the YZ plane first because, and actually I'm not going to draw all my traces, so I should back up for a second here. So here's my trace in the YZ plane. A nice looking parabola there. And then in the XZ plane, which is the one that's kind of coming out towards you, I've got a downward opening parabola. So it's going to kind of look like this. It's going to be not going to be quite as wide, right? I'm taking that parabola and I'm tilting it towards you like that. So it's going to look kind of like this. Right? Obviously, these things keep going. And then in the XY plane, I'm not going to draw them, but I would have like essentially diagonal lines going this way and that way, which I know is kind of funky. Well, let's draw the rest of the surface and maybe we'll see what's happening here. So actually, I'm going to draw, yeah. So I'm going to draw this because I know how to draw it. Let's talk about a couple. Let's talk about the level curve for a second. So let's say we went up 1, 2, 3, 4. So let's go up 4 units. So let's say we set z equal to 4 for a second. Well, if z is equal to 4, then my equation is going to be 4 equal to y squared minus x squared. Which you might not have a lot of experience graphing. When you have something like this, it's very, very close to looking like the equation of a circle. Right? If it was just x squared plus y squared equal to 4, we'd have a circle of radius 2. When it's x squared minus y squared or y squared minus x squared, we have a hyperbola. So when I'm graphing this, I know that if I let x equal 0, I'm going to get y equal to plus or minus 2. And then if x gets bigger, y can also get bigger. So if x is 1, y is going to be plus or minus root 5. If x is 2, y is plus or minus root 6, and so on and so on and so on. So what happens here is as the x values get larger, the y values also get larger. You get something kind of like that. I have not done the best job drawing. These graphs weirdly have slant asymptotes. But really the point of this is that if I go up to a height of 4, check it out. From here, I'm going to have this hyperbola. I should use a different color here. Going like that. And also to the left. And if I went higher up, I'd have another one. So if I keep going up and up and up, I have more hyperbolas. And the same thing also happens if you go down, right? If you go down negatively, right? If you let z equal, say, -4, then you have -4 equal to y squared minus x squared, which if we multiply both sides by -1, we get +4 equal to x squared minus y squared. So that's also going to be a hyperbola, but instead of opening up down, it's going to open left right. Because now you get to have the x-intercept being plus or minus 2. So this one looks like this kind of. Not at all. So yes, thank you. So this is xy, it's still xy. Again, good call. That's definitely a good idea. So now, instead of opening to the left and right along the y-axis, we're opening to the front and back along the x-axis. Which I know is not the way this is oriented, but it's the usual way we draw it. So I know it would be nice if we reoriented this like typically, but it's just not the way it's usually done. So right down here, right along here, I'm going to open out towards you and also away from you. So here's what this thing kind of looks like. It's actually what's known as a saddle. I've kind of drawn this a little bit too much of this to make it easy to draw the rest of it, but it's not good. Used to be better at drawing this. And literally called a saddle because it looks like a saddle. Like you could, I mean, this one's all right. And this can continue down this way. Okay, meets up over here with that. Right, it looks like the saddle like you would put on a horse. Or if you were out climbing or hiking, like when you if you ever hiked over a hill, like you hiking up, and you get to this little point here where you could go over to the other side, or you could turn right or left and keep going up and up. That's also called a saddle because it's literally a saddle shape. This is a saddle. And they're kind of neat. And this is one of the 6 quadratic surfaces that your teacher might expect you to be aware of. So generally, there's a few others. So, yeah, we got time. We got enough time. So let's talk about a couple other ones just because they're neat. So here's another quadratic surface. And maybe the one that's a little bit easier to visualize. X squared plus y squared over 9 plus z minus 1 squared over 4 equal to 1. This one almost has the hallmarks of a sphere, except we don't have the same coefficients on x squared, y squared, and z squared. This is kind of a sphere, but it's actually called an ellipsoid. An ellipsoid. So it's like an ellipse, except it's kind of been rotated around another axis. This is called an ellipsoid. Or, as I would rather say, a sphere is an ellipsoid where all of your axes happen to have the same length. This ellipsoid Well, let's talk about the center. Center of this ellipsoid is going to be x equal to 0, y equal to 0, and z equal to 1. Which is maybe less than ideal for drawing. There's the center of my ellipsoid. And then we can kind of find all the endpoints of the different major and minor axes by kind of seeing what x, y, and z would need to equal when the other ones were 0. So if x and y were both 0, z could be as big as 3 and as small as -1. So here's what I'm doing. If I set x and y equal to 0, and I have z minus 1 squared over 4 equal to 1. I have z minus 1 squared equal to 4. I have z minus 1 equal to plus or minus 2. So z is equal to 1 plus or minus 2, so that's 3 or -1. So basically, from the center, I can go up 2 or down 2. And I'm going to do the same thing for the other variables, except I should be a little bit more careful. I'm not setting everything equal to 0 exactly because I picked a different center. So I really should say, I'm going to set x equal to 0 and z equal to 1. If I do that, I'm left with y squared over 9 equal to 1, which means y squared is equal to 9, y is plus or minus 3. So from the center, I can go 3 to the right and 3 to the left. And actually, I'm going to do myself a favor here. And I'm just going to draw this oval right now. So here's my oval in the YZ plane. Let's see how well I can draw an oval here. Pretty good. Not the worst thing I've ever drawn. And then finally, not in the not in the XY plane, but in the shifted up 1 from the XY plane. Sorry, now I'm getting a little ahead of myself here. So setting z equal to 1 and y equal to 0, I'm going to get x squared equal to 1. X is plus or minus 1. So this is one that's going to be kind of hard to draw. I'm going to come out 1 in this direction, right there. I'm going to go 1 back. So just to clarify what I'm doing there, because I know it looks not lovely. I'm saying from this point here, from the point where y equals 0 and z equals 1, I'm moving forward 1 in the x direction and backwards 1 in the negative x direction. And I'm going to try and draw the oval that kind of hits that mark as well. So here's our ellipsoid. And the one I haven't drawn yet, which I'm about to, is this one right here. So those are my, well, 2 of those are traces, 1 of those is a level curve. So what's the difference between a trace and a level curve? Not a lot, actually, except the trace specifically refers to being in one of the 3 coordinate planes, either the XY, the XZ, or the YZ. Whereas a level curve usually means you're setting Z equal to a specific value and seeing what things look like at that particular height. So just to kind of say a little bit more here, our trace is in the YZ plane. We're setting x equal to 0. We're getting y squared over 9 plus z minus 1 squared over 4 equal to 1. And that's an oval. The center is 0, 1. And it's, well, in fact, let's draw it. I've already kind of drawn it though. center 0, 1, and you get to go. Sorry, that's looking. I guess that's. I feel like it's really small here. I guess it's not the smallest thing. You're going 3 in the y direction and 2 in the z direction. Let's try and use the same color, James. So that right there, that's in this trace right here. And then similarly in the xz plane, if we set y equal to 0, we're just getting the trace where x squared plus z minus 1 squared over 4 is equal to 1, which ends up being this red oval here, right? You're still at the same center, and then you're going 2 in the z direction, 2 up and 2 down, and 1 in the x direction. And then in the xy plane, things are kind of weird. You could find the trace in the xy plane. If we do that, you're going to get a slightly, like you're actually going to get something we haven't drawn, which is like this smaller oval here, because that's what's happening in the xy plane. And we can find that if we needed to. But really what's kind of more useful for drawing this picture is what's happening when z equals 1. So z equals 1, then we're left with x squared plus y squared over 9 equals 1. That's another oval where the center is the origin. And you can go 1 in the x. I've given myself not nearly enough room here. We can go 1 in the x direction and 3 in the y directions. Which is that red one there. No, the red. No, sorry, not the red one. This flat one here, apologies. So, graphing in 3D is hard. But it doesn't have to be super duper hard. Yeah. What the other thing I would say is that, what would I say? I'm trying to think about what I would like. I would say that if you're trying to graph things in 3D, I think starting with finding, I know what I should say in this last minute here. Something I kind of skipped over, which is important, is let's say we wanted to graph the following equation. And I got a minute. 3x plus 2y plus z equal to 4. In this equation, since everything is linear, right? Every variable is raised to a first power. That's almost always a sure sign that we have a plane. When we draw a plane, you really just have to draw or find 3 points and connect them up. So if I was drawing this plane, I wouldn't worry about my traces. I would find my x, y, and z intercepts. So the x-intercept, I'm going to set y and z equal to 0. I'm going to get 3x equal to 4, or x equal to 4/3. Y-intercept, same deal. Set x and z equal to 0. We're going to get 2y equal to 4. We're going to get y equal to 2. And for my z-intercept, we're going to set x and y equal to 0. We're going to get z equal to 4. And then you plot those 3 points. There's z equal to 4. There's y equal to 2. X equal to 4/3. You have to scale it down a little bit. So it's probably like right about there. And then we connect them up. Now, I recognize, and this is pretty common, that this is not the entire plane, right? We continue on and on and on. But often when we have a plane where the intercepts are positive x, y, and z intercepts, we only just draw that much of it. Like it's kind of hard to draw more of it because it looks kind of funky. You could try, right? You could kind of extend this out that way and that way and that way, but it just starts to feel like, where are you going to let this thing end? Yeah. So finding planes, drawing planes usually isn't too bad. And I would say that the kind of hallmark of a plane is you have some multiple of x plus some multiple of y plus some multiple of z equal to some constant. That's the usual plane equation. And sometimes we like to isolate z and just say something like z equal to ax plus by plus c. Where essentially you could take this equation and solve for z. You get something like this. All right. I said too much and also not enough, I feel like. I'm gonna look at that problem with the chemistry one. Again, apologies for not having thought it out a little bit more clearly. I'm sure I can make it work in just